Let's take a look at what we have so far as differentiation rules. We know that when we differentiate a constant times function, that gives us a constant times function's derivative. We know to differentiate the sum or difference of two functions, we get the sum or difference in their individual derivatives. We've also developed the product rule and the quotient rule. So next, what I want to discuss is how to differentiate the composition of two functions, how to differentiate f evaluated at g evaluated x. Well, let me give myself a tad bit of room. Now, I did talk about a function in x. To actually verify this, I'm not going to go that far and actually look at a full function in x. I'll just see what happens when I look at the derivative of such a composition at a single value of x. So to differentiate with respect to x, maybe f composed with g evaluated at a specific value of x, I'll call it a. By one of my definitions of the derivative of some function at a given value of x, I will look at the limit as x approaches a of this function evaluated x minus that function evaluated a all over just simply the inputs being subtracted. But I think that's the same thing as this. So allow me to insert a funky looking form of 1 as a factor to that difference quotient. The funky form of 1 I'm going to choose is this. After all, that divided by that is equal to 1, assuming they're not the same. Now, if you will allow me, can I just very quickly, I'm not going to write this, but can I very quickly refer to g of x as maybe a y? I'll think of g of a as, how about b? Now, if I take the limit as product and refer to it as a product of two limits, with that substitution, I have this factor next. Now, certainly, if these functions involved here are continuous, then certainly as x goes to a, y is certainly going to go to b. But if you take a peek at what I have right here, by definition, isn't that nothing more than f prime divided b? And over here, this limit evaluates to nothing more than g prime divided a. But I got to confess, I made the letter b up out of thin air to represent g of a. So you check out what this is really saying. It's saying to differentiate the composition of two functions, you've got the derivative of the outside evaluated on the inside times the derivative of the innermost function evaluated a. This is such a big deal, I'm going to now rewrite it in terms of x not a, and I've got a name for it. This may be the product rule, this may be the quotient rule, but this is what I refer to as the chain rule. To differentiate such a composition, I differentiate the outermost function, evaluate it on the innermost function, times the innermost function derivative. Again, I'll refer to this as my chain rule. So let's see if we can put it to practice. So let's go ahead and let y be something like, how about the cosine evaluated some quadratic beast? So for me to differentiate the composition of these two functions, I differentiate the outermost function first, but to differentiate the cosine of anything, I get the negative sign of that thing. The innermost function g of x does not change. But the chain rule says I must multiply by the derivative with respect to x of the innermost function. But its derivative is nothing more than this binomial. And I have to admit, I did waste a little bit of time. Technically speaking, I typically don't write that out. I just simply differentiate directly and write the answer. There's our first application of the chain rule.